Okay, this morning we have several talks about the quant-scaling techniques, and this afternoon we are going to have several talks about applications. And so the first presenter is Professor Roger Stone from University of South Queensland. Let's welcome Professor Roger Stone.
Thank you, Mr. Chairman, and for the organisers for inviting me to this wonderful occasion. And this talk will be something completely different. I'm going to be speaking on applications and also from the user's perspective, much more than perhaps we've heard through a lot of the very good discussions so far. So this is taking our approach that involves the users and very much how we connect this type of information into their management decisions. So it's a little bit more than impacts. I need to acknowledge my associated group, which is the World Meteorology Organisation with the Commission for Agricultural Meteorology, and my colleagues. So the outline today is that I'm going to discuss the already existing high levels of climate variability in Australia and the long-term shifts. So this is the outline of the talk. Linking climate forecasts and projection information to management decisions across all timescales. The key words there are management decisions. The value of integrated approaches and the value of crop simulation models to help in that integration in particular. So there's issues of scale in there. And recognising the importance of the entire value chain in agricultural production, which goes beyond just our friendly farmers, but right through to the export agencies, insurance companies and so on. And the value in utilising seasonal climate forecasts, which is where we have a lot of our background work in my centre, and then taking incremental shifts based on the improved management systems that might become available through use of seasonal forecasts. Providing outputs that are relevant to agriculture, especially extreme events, heat stress for cattle and animals. Then I'll finish very quickly. I have to speak very quickly because I have too many slides, unless I get special dispensation, probably not. So first of all though, to explain where Australia is, this is how Australia sees itself in the world, on top of the world, not down under, right? So we are up there, and not many people realise that, but it's, especially when we're playing cricket, we think we are the best, right? But also, it's intrigued me by looking at this different perspective, is how much Australia is surrounded by major oceans and how much we're influenced by shifts in sea surface temperatures in the Central Pacific, Equatorial Pacific, the Indian Ocean, the Southern Ocean and so on. It wasn't until I flipped it over, until we did this, that I realised quite just how important that is. In terms of variability, Australia ranks the highest in terms of year-to-year variability, taking I think the 90th percentile minus the 10th percentile divided by the median. And then we have South Africa, Germany, France and so on, and China perhaps about half of our variability. And importantly, the variability is increasing, particularly in the grazing areas where a lot of our cattle and sheep, pastoral areas, pastoral growth areas, you can see there. So the variability is increasing and it's high already. There are also long-term shifts. This is just a 60-year appreciation of the sort of long-term shifts in millimetres per decade since the 1950s, but importantly, this is importantly, you can see the areas shaded orange or dark brown there on the eastern side of Australia, which are undergoing some of the major shifts. But that's very important agricultural production activity, and in southwest Western Australia. Oh, thank you so much. Otherwise, let's set the lights out. So we can see here, and this is very important. Grazing land and also sugar production. I come from a town here near Brisbane, and this is the major population centre and growth area in Australia, and southwest Western Australia, major wheat production zone. Massive bushfires occurring, I believe, today in this area, which is suffering a major shift in rainfall. But the downwards, but notice because Australia is a particularly large country, there's virtually no one living in it, we have very high or increasing rainfall in the northwest of Western Australia, which is our major energy and gas fields and so on, and mining operations occur in this part of Australia. So it's a mixed pattern across the country very much. If we take it to the next scale, if we integrate this with, in this particular example, a grass production model called Aussie grass, which is very appropriately named. This is percent change in components of the grazing system simulated through Aussie grass. We can see change in pasture cover through this period is roughly the same as the rainfall decrease, but not quite the same. There's something else in here due to temperature or soil moisture conditions. But if we look at pasture growth as opposed to cover, then it covers a much larger area of Australia. So it's very much important to integrate the whole system, soil moisture levels, radiation levels, temperature and so on, into this type of understanding. Also major shifts in maximum temperature and minimum temperature. Minimum temperature particularly important because of the impact on frost, but also on cattle well-being and feedlots and intensive grazing systems, understanding the need for cattle to cool down at night. Am I speaking too quickly? Australians tend to speak too quickly. So if anyone says I'm speaking too quickly, let me know. I'll slow down. Okay. So we get into trouble for that. This is the interesting aspect though. So there's some opportunities associated with these shifts in climate. This is the date of first and last frost. The date of first frost is now roughly now 26 days occurring later in this particular region where there's a lot of grain produced. So the date of first frost getting later and the date of last frost getting earlier. So there's virtually, this is for 2 degrees in the screen. Virtually no frost occurring at this level in this particular region in Australia. So it's a benefit to wheat producers in this part of the country, provided we could continue getting enough rainfall. But at least in terms of frost, there's some opportunities there. There's not quite so much damage due to frost, and a change of varieties might be allowed there. But this is perhaps one of our main points, and that is we've taken a whole of climate approach. We haven't just approached the climate change issue in isolation. In this particular figure, we have a listing here on the right-hand side of some well-known climate systems that we're all probably familiar with. This is not exhaustive. There are some others here as well. The well-known intraseasonal pattern, the MJO scale, the seasonal, ENSO scale, interannual, biennial, quasi-biennial oscillation, decadal Pacific oscillation perhaps, the IPO, multi-decadal patterns and climate change, and we could probably include the Indian Ocean dipole and southern annular mode in there as well. But also on the left here you can see some decision systems that are associated with these various timescales. This is particularly important because the managers of these systems work according to their immediate requirements. So tactical management decisions such as fertiliser and pesticide use might be very much tied in with the time sequence of the MJO. Very well understood in lots of northern Australia. The MJO, notice there's a very good poster on the MJO outside. Very important system, particularly for tropical Australia. Also in the extratropics. It's surprisingly how much the farmers and others are using information related to the MJO for tactical decisions, but then more strategic decisions, perhaps what variety, what type of plant they will grow for the coming season, which might be linked to ENSO. Some industry decisions at decadal scales, so for the sugar industry that we work with, particularly interested in their large-scale storage systems, but they will need decadal forecasts. And then we have climate change issues as well. So I say to the climate change skeptics, it's not a matter of is it natural variability or is it climate change, it's all of it together. Okay? And of course there's the intersection of these. There's very high levels of variability and then there's the climate change glove on there as well. But the decisions that these various industries make seem to fit quite well into this sort of timescale, and this becomes a lot more transparent to industry users once we start to describe these other systems, rather than just talk climate change or just talk, say, ENSO scale. The other important point is to understand the whole value chain in agricultural production. So when we're linking climate information, climate forecast information, climate projections, seasonal climate information, one mistake we made actually was to do all the work here at the farm level. This is the farm level where the issues may be scarce, use of scarce water resources, decisions on farm to help the farmers. Unfortunately though, there's another major group here called the milling group. These are all chemical engineers usually, or agricultural engineers, quite a different group to these. There's the harvesting group in here, and then there's some very important marketing and shipping agencies that sell the crop internationally for exports. And they have decisions related to likely sugar quality, in this example for the sugar industry, forward selling based on likely crop size, and large long-term strategic decisions. If this group is left out, then the system will, the whole value of incorporating climate information can collapse. If the major export agency using seasonal forecast, or doesn't use seasonal forecast information and sells a crop that cannot be harvested, that has a major impact on the entire industry in this particular example. So you have to address all these issues that we have been discussing the last few days right across the value chain in just this one sector of agricultural industry. If you leave one sector out, because it all feeds back on itself there, then the entire industry can have major damage. In Queensland Sugar Limited, for example, lost $500 million in 2010 because they had no understanding of the 2010 La Nina event. The farmers knew, but the export agency did not. Huge impact. So that applies to seasonal work as well as climate change information. To help make this transition, we use crop simulation models. This is a field scale, which is a challenge. This is where there's the output from this particular example is called APSIM, Agricultural Production Systems Simulator. It has precise daily time step model inputs that mathematically reproduce the physical processes taking place in the cropping system at this sort of field scale. Mind you, our fields in Australia can be very large, but the value is it can then provide an output, a seamless output of yield or potential yield or a probability distribution of yield, and understand also a lot of the processes that are taking place to improve our understanding of key soil processes, and also then introduce a range of management options. Very important, so we can simulate various management options. There's the APSIM model, for those that like models. Climate is one small but important component. We incorporate climate change information, or particularly seasonal forecast information, seamlessly into the model, and that has all these characteristics, the biological, biophysical components of the crop model, the competition between pastures and crops, there's soil water inputs, soil nitrogen, and so on. Needs daily inputs of temperature, radiation, evaporation, and precipitation from the forecast. And that can produce outputs that this is an example using ECMWF UK Met Office seasonal information, where we're using outputs, or we run APSIM for each of the ensemble members for the last 30 years. But the output then could be biomass or sucrose in the case of sugar. Could also adjust management decisions associated with a particular crop. This is during an El Nino year and particular soil and moisture conditions, and you can see you get different yield. This is yield value here, based on the information supplied by APSIM and climate forecast information. I'm using climate forecast information deliberately because we believe we can use climate forecasts on a seasonal basis to help users make incremental advances in their management. And if the forecasts are anywhere near accurate, then over time they will start to adjust their operations and their management systems and their cropping systems and their farming systems. And in climate change, for example, may produce more dry conditions in Australia, and if the seasonal forecast can pick this up, then that will then be reflected through day-to-day, month-to-month outputs, and the farmers will start to make incremental decisions almost without realising it. So that's one of the subtle, I suppose, approaches we're taking. There's always this challenge between climate model outputs and the crop model. The scale issues are particularly important. So at the moment we prefer to use statistical downscaling approaches rather than dynamical, and that's particularly to pick up some of the extremes that are known within the system and represent that within the distribution. Or within the crop models, we pretend the farm is maybe 100 kilometres across and so on. So we try to scale up from the crop model, or make the crop model perhaps less sophisticated. But the scale issues are particularly important, and we're not quite there yet on working through that. Very important for us is to have a fully integrated system. This has already been picked up, I think, in some previous talks, especially with the general circulation model selection. This is climate change projections for a reservoir system in southern Queensland. And we have taken this best model approach, although we use the most preferred model, using demerit point, demerit points on how well the models can or cannot reproduce mean sea level pressure variability, seasonal rainfall variability, major systems, major rainfall variability, or temperature patterns within the region. Then we have empirical statistical downscaling, so we can maintain the original model statistical sort of distributions there, as the previous speaker was alluding to, particularly the extremes, which are very important in a river sort of system. Link that to a hydrological model. But down here we have a reservoir alteration model, which has a crop modelling component as well, in terms of the demand for water coming out of that reservoir. And then if you can find a good economist, then we have an economist there as well to have an economic input. So that's the ideal. And we're doing this for the cotton industry at the moment. It's picked up, I think, a lot of the discussion that we've had so far at this meeting. But that's very important. It has to be a fully integrated system, including economics, if we can tie that to that sort of level. And finding those sort of models is particularly difficult. Just some of the climate change projections. This is the state of Queensland where I am, and we ran these models forward. They all show about a 2-degree warning. This is for 2030, 2040. We found much more cohesive results if we made it January to March, by the way, instead of the usual December, February. And we found this particularly so in changes in precip, and we can see that January, February, March shows an increase in precipitation in a lot of eastern Australia. This is just using 5 or 7 models in this particular example. The rest of the seasons showing reduction in rainfall. So the annual values mask the important seasonal variability in here. But it's also important to have outputs such as solar radiation and other outputs that are important for agricultural production. So these include precipitation, of course, in this example, increase in summer but decrease in other seasons. So that may benefit some crops compared to other crops. Okay. But also solar radiation, an increase overall, a decrease in wind speed, which is particularly important in what we call the feedlot areas. This is a feedlot, if you can see that there, where 20, maybe 30,000 cattle are all together in a very intensive farming system. So a decrease in wind, an increase in temperature, an increase in relative humidity has a massive impact on animal health and animal well-being and stress. So this is a particularly important point. So our particular outputs actually suggest an increase in humidity in critical summer months, a decrease in wind flow, especially in these regions, increase in solar radiation. And there's huge industry investment in this type of cattle production, which we believe is set for disaster. Drought issues are particularly important in Australia. This is from Julie Outlaster and Alexander, 2009. You can see that there's an increase in this particular model output. This is CMIP3, showing an increase in warm nights, and which is very important for an industry such as the cattle industry, where the animals cannot recover from the heat of the day. So we have an increase in high temperatures during the day. It's not so bad if there are cool temperatures at night, so the animals can recover. But with warm nights, that does not allow that to happen. So that's a major issue. And this is also heat wave durations and so on. So the outputs from this type of modelling, particularly important to agriculture in terms of drought potential and hot nights and so on. Also looking at the extremes, this is important, I believe, that a 10% decrease in the mean annual rainfall in Australia actually has major implications on the extremes. This decrease roughly doubles the risk of exceptionally low rainfall in 5 of the study regions in this particular example, particularly Victoria, Tasmania, South West Western Australia, and these are major agricultural production regions. And for Gabrielle's point, I thought I'd pull this slide out as a benefit. The numbers of days exceeding 35 in major zones, roughly to increase about 100% in major regions in Australia by 2070. And about 50-60% increase by 2030 in these particular locations. So we are particularly concerned about this increase in temperature. If we run an agricultural production model though on wheat yields, and this because now we're incorporating the uptake of carbon dioxide into the plant. How's my time going? It's okay. It's not so bad. This is for the wheat crop in Australia 2020 and 2050 with low and high scenarios, emission scenarios. And but if you include the uptake of the carbon dioxide into the crop, and also the fact that an increase in, remember I mentioned there's an increase in summer precipitation, which allows the soil to store more moisture, and that stored moisture from summer will help the crop survive the coming winter. So it's important to take that whole approach, not just the in-crop growing rainfall during the particular growth stage of the crop, but to include the antecedent moisture from the previous summer rain. when we do that, there's only in the high scenario 2050 output. This is just using the CSRO model, by the way, not the range of models we would prefer. But for this particular example, it's showing the importance of understanding all the factors. The fact that you could increase summer rain will store the moisture in the soil to help the crop survive the dry winter periods ahead. So it's not all bad news for an industry like the wheat industry. And Australia is one of the world's largest wheat exporting nations. Move along. In terms of heat load for cattle, we found extreme opportunity using 20th century analysis to reassess back over the last 100 years of extreme heat load. But the results show that in the Darling Downs region, which is in southern Queensland, the accumulated heat load, because this allows for accumulation of heat over a number of days, has reached extreme levels on 6 occasions, and the number of higher extreme values particularly seems to be increasing. And this includes this interesting issue of the need to recover from high overnight temperatures, and the fact that that's going to not be the case in the future has this important implication. And this is where we introduce some of the seasonal forecast outputs. We've been running seasonal forecasts for the last 20 years operationally through my own group, through to the Queensland Government, but also with the Bureau of Meteorology, published back here in 1996. But this is showing forecasts of maximum temperature on a seasonal basis, minimum temperature, and also the chances of being the top 20% rather, top 20% of relative humidity, top 20% of overnight temperatures. You can see immediately the seasonal forecast can give warning of these particular sort of extreme events as for an industry such as the cattle industry. So we're assessing and suggesting that we can make users can take incremental adjustments based on these forecasts to be much more aware of the likely future as these forecasts continue to be issued. I'll move along here. My last section here, since I have 5 minutes, 5.5 minutes, and these are some examples now of adaptation to climate change and some of the agricultural examples. So I'll move through this fairly quickly. This is a good particular image, I guess, that shows the plant breeding programs as being particularly useful in the adaptation to climate change. This particular variety of maize survived tropical cyclone Larry, which I believe was a category 4 or category 5. This particular type of crop is particularly prone to rust. One variety, because it was prone to rust, could not survive the impacts of the tropical cyclone, but the other variety could. So assuming we have more intense tropical cyclones, with maybe fewer of them in the future, then choosing the appropriate variety is very important. So there's one simple adaptation. These are the others, and based on the time I have, I'll skip through them quickly. There's some commonalities. For the grains industry, there's the development of varieties with appropriate thermal time and CO2 or volatilization requirements, varieties that can withstand heat shock and drought tolerance. We already have some of these, stay green wheat and stay green sorghum. Resistance to pests and diseases are particularly important. Alternate planting rules to be more opportunistic, such as now we have reduced frost risk, change your planting rules, develop further risk amelioration approaches, zero tillage, storing more moisture in the soil, not ploughing out the soil quite so much, and so on. Provide tools and extension to farmers. This is an obvious one. Analyse value chains in the whole of the agricultural system. Don't just rely on information going to farmers. For the cotton industry, similar sort of outputs here. Select varieties with appropriate heat shock. Heat shock tolerance seems to be the key requirement. So we have a major challenge to the plant breeders and so on. Improve whole farm crop water use efficiency. Investigate crop production in parts of Australia or other regions of the world which might be useful for cotton production. Conduct research into avoiding resistance to pests. And for rice, I'll just about finish, Mr. Chairman. Invest in more efficient irrigation methods. I have lots of these to say. Consider cost benefit reducing water conveyancing through irrigation. Develop approaches to managing water resources that take climate change and seasonal decadal drivers of climate variability. Understand this long-term, these other high-frequency modes. I'll skip too crazy. So my key summaries and issues are these. And this is what we've just discussed, that Australia has the highest level of rainfall variability in the world in terms of a major, large landmass, and this variability is increasing. So understanding variability as well as long-term shift is particularly important. We've had major shifts occurring in temperature and precipitation. In agricultural production, recognise management responses to all these temporal scales in agricultural systems. Understand that that's how they work. Agricultural management operations work on various time scales, and climate change will be one of those important features. Address issues across the entire value chain need to include integrated climate agricultural modelling systems. There's value in such aspects as 20th century reanalysis. There's value in using seasonal climate forecasting to assist capability to manage increased levels of variability and to assist incremental shifts in agricultural management on a year-to-year basis. And there's more. Utilise options and extensions and enhancements of existing systems. Don't necessarily start with something completely new. There may be good opportunities to adapt current systems. Use it in a participating way with industry. Have them at meetings like this. Major industry groups and agricultural industry groups would appreciate that. Develop crop varieties with appropriate thermal time and resistance to heat shock, and whole farm management and whole farm systems, and improve breeding and management of animal heat stress where livestock are handled in intensive areas. And that's my talk. Thank you very much.
Very interesting talk. Thanks for sharing your integrated system with us. So we have time for a few quick questions. Are there any questions or comments? Yes.
It's very interesting you suggest to make use of this seasonal forecast. But what happened in the places like Taiwan? We have very low skill in seasonal forecast. So it somehow it's difficult to convince people how to use the so-called climate information.
I think that's a good point, but it's worth a second look at the skill, I think, in seasonal forecasts in some regions. I think, and there may be a good opportunity to use forecasts at the intra-seasonal scale, such as the MJO. I notice there's a very good MJO poster. So maybe that's a start, so that there's an understanding, of the various temporal scales in climate patterns. But I would offer the suggestion it's worth a second look at the seasonal forecast capabilities and to further research that opportunity.
You emphasised the importance of the whole value chain. I just wondered, in terms of the service of seasonal forecasting, whether who was taking it up, and was it being provided as a private service, or is it provided by the state government, or how's information delivered, and who's most interested in it?
It's a good question. It's both. The state governments and the governments tend to favour the growers and the farmers as being seen as a large voting base, perhaps, and also obviously in need because there's many farmers there. But the important end of the export agency or we'll say export and trading groups needs a different approach, and perhaps private industry is best placed to work with that very exact, very timely need. But unless the both are covered, we have realised that then the system can fail. The whole system can fail. So in the example I showed, in Australia, for example, a lot of our funding for this type of research comes through research development corporations, which take a levy on the side of the various agricultural outputs for wheat and for maize and for cattle and cotton and so on. And that tends, because it's mostly grower-based, the benefits go back to the growers, and they have missed this very important group that export the entire crop. And if they make the wrong decision, then that damages the industry in a massive way. So that's been a wake-up call for us, and now we are working around the world with those agencies now more than we are with the growers. You have to keep both. And it's a different language, you have to dress it differently, you have to approach the issues quite, as you know.
Actually, my question is similar to the previous two, because in Taiwan's experience, I think probably that's the chain is too short. So, for example, the seasonal forecast product is not supposed to be used as a weather forecast information. And so, in other words, that is not a forecasting information that can be used by general farmers. Maybe we need some kind of mediator in between to communicate the information to the users. But you just explained that maybe in Australia you have the big agencies or corporations to do this type of research and try to translate the scientific results to the user effect. And then my another question is that you mentioned several times about the net incremental adjustment. Could you elaborate a little bit on that and how the users can use this seasonal forecast product to make the incremental adjustments? Yeah.
So if we, thank you for your question, if we assume that we have some good skill and accuracy and the forecasts are mostly in the right side, so forecasts of particularly dry or hot weather or hot seasons that way, and assuming that's going to be the norm in the future, then as those forecasts are produced month in, month out, for 3 months ahead, 3 to 6 months ahead, 3 to 6 months ahead, and then the next year the same thing is almost reoccurring, or the following year, then the farmers, for example, will say, another year like that, I will now switch from wheat to chickpeas. So they've started to make adjustments based on the forecast. And in fact, the climate change projections say that's what they should be doing anyway. See how that works? So, getting back to your first point then, yes, you need specialist extension agencies that can bridge that gap. But we have some workshops called Managing for Climate and Weather workshops. And the users have to list all their decisions as they come in the room at various scales, and then start to understand how both weather forecasts and seasonal climate forecasts and climate change projections can interact with all those decisions. It takes about 1 day, and they're very effective workshops. But you need specialist extension services, or you can have private extension agencies that are looking at steel. You can have that as well, that can come in and run these workshops. And that gives the user ownership. And they particularly enjoy having top scientists come along as well to speak, so they can get firsthand what's going on. And then they get ownership. Then if they're making major decisions that could affect the rest of their lives, or an industry worth billions of dollars, they're much more likely to make that decision if they have a thorough ownership of how the system works or doesn't work.
Okay, because of time constraint, I need to move to the next speaker. Let's thank Dr.